Welcome to part 2 of our video series on parent functions. Now, if you watched my first video on parent functions, you may be a little confused because now I'm calling them parent functions and the name of the video is parent functions and parent functions too, but I never told you what a parent function actually was or why it's called that. And there's a good reason for it. And I'm still not going to tell you quite yet, but we will get to that in a minute. The idea is, in this video, we're going to take the functions that we learned last time, those pictures that I introduced you to, and we're going to take those and move them around and manipulate them and things like that. So yeah, if you have the graphs that we did from last time, the quadratic, the cubic, the square root, absolute value, and cube root, if you have those 5 equations drawn, have those notes ready in front of you because you're really going to need to reference that a lot as I go through this video. And if you haven't seen that video, go back and watch it and make sure you have those graphs drawn before you go through this one. All right, let's just start graphing some stuff. I'm going to throw this at you. And this may look a little scary, and I understand. We're going to be graphing things that look kind of like this. Now let's use the method that we used last time. And the method we used last time was we took numbers and we just started plugging them in because we didn't really know what those shapes were going to look like, right? We didn't know what they were going to be. But if I start plugging numbers in, I'm going to get a good idea of what that shape is. So let's pretend I don't know anything about this and just start plugging stuff in. So let's make a chart. I'm actually going to start from 0 this time. There's a good reason because I actually know what this is going to look like, but just trust me. Let's start from 0. Let's start 0, 1, 2, 3, and 4. That should be enough. Let's just start plugging numbers in and see what happens. So if I plug in 0, that's 0 minus 2 squared minus 4. So if I plug in 0, I get, well, that's negative 2 squared minus 4. Negative 2 squared, that's negative 2 times negative 2 is 4 minus 4. That gives me 0. So when I plug in 0, I get 0. Okay, so far that seems pretty normal, even as ugly as that equation is. All right, let's plug in another one. Let me get rid of my work done here. Now, if you'd like to go ahead and fill this chart out and graph it, that would be a really good idea. Why don't I go ahead and suggest that? If you would like to, pause the video, plug these numbers in and graph them and see what you see. Either way, I'm going to go through it for you. So let's plug in 1. So if I go 1 minus 2 squared, all right, 1 minus 2 is negative 1 squared. And negative 1 squared is 1 minus 4. What is 1 minus 4? It's negative 3. So in my chart, I get the point 1, negative 3. That means when I go to the x position of 1, I go to the y position of negative 3. Okay, kind of seems random, but let's just trust that our math is correct and just keep going. All right, let's do the next one. Let's plug in 2. 2 minus 2. It's a terrible 2. Let me rewrite that. 2 minus 2 squared minus 4. What's 2 minus 2? Well, 0. That's 0 squared minus 4. Well, 0 squared is just 0. 0 minus 4. What's 0 minus 4? That's just negative 4. So when I plug in 2, I get negative 4. So that's going to be the point down here. All right. Still really don't know what's going on yet. But let's just keep plugging away because we know that even if we don't know what's going on, we can still plug numbers in and still get dots and still get a picture, even if we're ignorant and don't know, what this is going to look like ahead of time. All right, let's plug in 3. 3 minus 2 squared minus 4. Well, 3 minus 2 is 1. So that's 1 squared minus 4. 1 squared is 1. 1 minus 4 is, interesting, negative 3. I've already got a negative 3 on my chart. Well, let's plot it. So if I go to 3, which is right here, I get the number negative 3. Well, let's keep going. Let's see what happens. Let's plug in the next one. Feigning ignorance is actually quite difficult when you've done these for a long time. 4 minus 2 squared minus 4. All right, 4 minus 2 is 2 squared minus 4. 2 squared is 4. 4 minus 4 is 0. That's interesting. I've already got a 0 on there too. Where is that going to go? Well, it's going to be the 0.40. If you take a second and you look at that, it might look pretty familiar, especially if you have the notes up from the last video. Because this is starting to look a whole lot like something we graphed last time. It's starting to look a whole lot like a what? A parabola. And in fact, it is. All right? And remember last time we graphed the parabola and it was y equals x squared. Well, look. This has a square in it. It's not exactly x squared, but it has something that is squared. And it doesn't have any other powers in it, but it does have that square. So this is still, in fact, going to be a quadratic. That's not how you spell quadratic. Quadratic. So this equation, even though it doesn't look exactly like the last one, it still has a square in it. And if you were to multiply all these things out and work it out and simplify it, you would get an x squared. And in fact, it does look like a parabola, just like the one we did last time. But there's a difference here, isn't there? What's the difference? Let me get rid of some of this stuff so I can have some more room to work. Notice, this is the same exact shape. If you have your notes in front of you, you'll notice not only is it the same shape, but it's the same configuration. Like this dot and this dot are still the same relationship to each other. And this one and this one. The dots are in the same place, except something's happened. They've moved. Look at this dot here. This is the bottom of the parabola. This is actually called, it's got a special name. For a parabola, it's called a vertex. You may have heard that if you've taken geometry or something, usually means like the corner of something. But in this context, it's the bottom of that U shape, that parabola. That vertex is at the coordinate. What coordinate is that? That is an x value of 2 and a y value of -4. Now, if you haven't caught on to what's going on yet, take a look back at that equation. Where do those numbers appear? Well, there's a number 4, quite obviously here. Let me actually write this underneath it. Oh, there's the 2 and there's the -4. That's the coordinate. That's where that original point, that vertex ended up. Well, there's a 4, or -4, and there's almost a 2. That's actually a -2. Well, if you think, we've done this before. Do you remember when we did point slope form? That's the slope for, it's a line equation, right? And you had an equation that had a point visible and then the slope. This is the exact same thing. Notice or remember that it didn't have the square up there, right? But the square was gone. But you still had this parentheses business, and you would change this sign, and you wouldn't change this sign, and it would give you a starting point. It turns out that it works exactly the same way. So you don't actually have to plug in all those numbers like I did a few minutes ago. I wanted to show you where those numbers came from so you could see what happens when you actually calculate them. But if you know this shape and you know where to start, you could just graph it. And it works exactly the same way as point slope form does. And that is the miraculous thing about parent functions and the way we're going to, which I still have to define in a minute, and the way we're going to graph these things, okay? All right, let's do another one. Let me show you another one. Let's do x plus 1 squared minus, I don't know, let's say 3. Now, working on our hypothesis that this is the same as graphing things in point slope form, let's just blindly do that. I'm not going to start plugging numbers in, okay? Now, don't get confused here. I'm not plugging numbers in because I have a hunch that this might be the same because I noticed a pattern, didn't I? I noticed that the pattern is if I change this sign and don't change this sign, that's going to be where my parabola starts. So if I go left 1 and down 3, that gives me my point. This, in theory, should be my new vertex. That's my new starting point for my parabola. All right? Now, how do I come up with all the other points? Well, I could plug numbers in. I could start plugging numbers in and getting heights and things like that. But again, it's the exact same shape. So I don't have to plug in. I can't make this clear enough. Once I get this point, because I know this pattern, I don't have to plug in any more numbers because I know, and I've already memorized, and then maybe you need the notes, but you've got them next to you. You already know what the shape of a parabola is going to look like. You know that wherever it starts, it's going to go over and up 1 on the right. And on the left, it's going to go over and up 1 like that. And you also know that from this original point, if you go over 2, you're going to go up 4 to get to that next dot. It doesn't matter where it is. It doesn't matter that that's at 1, 1. I don't care. I care that this is the same amount over and the same amount up as the original parabola when you draw. Same thing on the left side. I know that this is, I didn't mean to get rid of that. I know this is symmetrical, right? You know that the U is symmetrical, left to right. So I know that if that dot's over there, then this dot's right here. It doesn't matter that it's the coordinate -3, 1. You could figure that out if you plug numbers in, but again, I'm not doing all that because I have recognized the pattern. Then I can start down here at -1, -3. And I know what the shape looks like, so I'm just going to draw it. And that's as simple as that is. It's that easy. So recognizing that this is the same thing essentially as point-slope form in that you can find this point and then graph it, allows you to do these things without plugging in all these numbers. You just are taking that original function that was in the center and moving it. And that's the idea of a parent function. A parent function is going to be that original graph, that first one that I drew in those last videos. And you can think of it as that's the parent, and all the children graphs, if you want to say it that way, are all the ways you can move it around and manipulate it. So this would be a child of the original parent graph, if that makes any sense. So a parent function is the most basic, the original. It's the father figure, the mother figure, however you want to think about it. That's the original one. It starts in the middle. I can actually draw it for you. So the original one was here and here and here and here and here. And that gave you this shape here. That's the parent. And all the children are just, it's a weird way to say it, but that's kind of the idea, is that if you move it around, it's still going to be the same looking shape, just moved, right? All right, let's try another one. We're going to do tons and tons of these things. This video might end up being quite long, but I feel like it's important to have lots and lots of examples because there's a lot of different, variations you could see with these things. Why don't you try this one? Let's do this. I don't remember what the last one was, but it probably wasn't this, so we'll go with that. All right, pause the video and try that one and come back, and we'll see how you did. All right, so I'm going to change this sign, -4. Don't change that sign. Again, don't make this complicated because we know the patterns now. We're going to go left 4 and down 1. That's the coordinate -1. That's my new vertex. I'll even name it that way. This is my new coordinate. And again, I don't care what the other points are. I just know that they are the same relationship to this original point. So I'm going to go ahead and draw these 2 points just like that. This is more art than it is math, really, at this point. I'm not doing any calculations. I'm just drawing dots because I know how far away to draw those dots, right? And then I draw my curve. And I'm done. That's it. Really, really is that simple. So this is why I really wanted you to memorize those dots from the functions last time. Because once you know them and you know the relationship and how they fit on a picture, you can just move them around and you are able to graph all kinds of things from that. All right, let's try one that's not like this. How about this? Now, if I were to plug some numbers into this, I want to prove this to you. And you could just graph it, and if you have an idea of how this works, you could just do it. But I do want to prove some things because it does help. If I plugged in the number, let's say 1 into this, that's 1 plus 3 square root minus 2. Now, remember, I'm not asking you to do all these things. Remember, the whole point of this video was to not plug numbers in, but I do want to prove this to you because these questions do come up in class quite a bit. If I were to plug in this number, 1 plus 3 is 4. Square root of 4 is 2. 2 minus 2 is 0. So if I plug in 1, I get 0. And let's plug another number in. I'm being very strategic about the numbers I'm plugging in. It may seem like I'm picking them out of thin air, but I do know why I'm plugging them in. It's because I know what this picture is going to look like. Don't dwell on that too much. Point is, I'm plugging numbers in. Let's plug in negative 3. If I plug a negative 3 in, oh, that's a 2. What do I get? Well, negative 3 plus 3 is 0. Square root of 0 is 0. Minus 2 gives me negative 2. Now, here's the issue. Some people say in class, and I see this all the time, is that, well, you can't take the square root of a negative number. That's true. But when you do things to it, it doesn't always end up negative, right? Like I plugged in a negative 3, but I still added 3 to it. That's why you can do that. All right, so the point is, I plug in negative 3, I get negative 2. What if I plugged in negative 1? Let's plug in negative 1. Oh, that's not right. Negative 1 plus 3. Well, negative 1 plus 3 is negative. Oh, sorry, it's not negative at all. It's 2 square root. Wait. I don't want to do that. What do I want to do? I want to plug in negative 2. Did I just say negative 2? Yeah, but I didn't write it. My bad. All right, we're going to plug in negative 2, not negative 1. Let's plug in negative 2. All right, it's late. Negative 2 plus 3 is 1, right? So what is the square root of 1? Well, it's 1. And 1 minus 2 is negative 1. So if I plug in negative 2, I get the number negative 1. Now, I told you that we weren't going to do all that stuff, but I wanted to prove to you that this, in fact, does work for other functions. Because look, if I were to draw this, that's the exact same shape as the square root function, this one here, that we did in the last video, right? It just starts in a different place. And where does it start? It starts at negative 3, negative 2, which you probably should have guessed from the beginning because look, if you take that and you switch it, and you don't switch that one, you get negative 3, negative 2. And if I seem excited, it's because I am, because I think this is really cool. This stuff actually works this way. And it's just absolutely amazing to me that you can take these basic functions and it works the same way, whether it's a line, whether it's a U-looking parabola thing, whether it's this square root hook-looking thing, whatever you want to call it. It always works. And it's a beautiful thing. So do I expect you to plug numbers in to get those dots? No, I don't. What I expect you to do is to find this point first and then find these points because you've memorized their positions and then just draw it. That's what I expect. All right? But I did want to prove to you that just like with the parabola, this works this way too. It's amazing. Now, I don't have parentheses here, but it works the same way. All right, let's do it. Let's do another one now that you've seen that. I've been doing this for a long time. I've graphed hundreds and hundreds of these things, but it still blows my mind that it works. And I know why it works, but it's still a beautiful thing. All right, I'm over it. Let's do that one. You try that one real quick. Give that one a shot, and then I'll do it and see if you get it right. All right, so this time we're not going to plug in any numbers. We're just going to say, well, let's just blindly do this. That's 1 because I switched it. That's 3 because I didn't switch it. Where is that? That's the point right here. That's the coordinate 1, 3. And I see that this has a square root in it. That means that it's going to be the same shape as the y equals square root of x function. The parent function, if you will, is this one. And I'm just taking that parent function and I'm moving it somewhere else. All right, so what did that parent function look like? Well, if you've got your notes in front of you from the last time, you'll remember that it goes over 1 and up 1. And then from the original dot, it goes over 4 and up 2. Right? And then you start from this bottom left one, and you get this shape. Look how easy that is. This is so easy. I'm not putting in a lot of numbers and calculating things. That's not what this is about. All I'm doing is I'm just taking the same technique as I used for point slope form, and I'm applying it to all these other shapes, and it really does work. Right? It's almost a miracle. So that's how that works. Let's do a different one. Let's do this one just to prove to you that it works on all of them. Y equals, you try this one. See if you can do this. X plus 4 minus 2. Oh, that wasn't right. All right, try this real quick. All right, just like all the other ones, change this sign. Don't change this sign. It works the same. I can't make this any clearer. Don't treat this as anything different. Now, again, this is not parentheses. It's absolute value, but you can treat it like the parentheses that you did before. So the point is it's in there with the x. If I go left 4 and down 2, I get this point here. And then I'm going to remember that the absolute value looks like a V shape with these 45-degree angle lines coming off of it like that. And that's what that looks like. And you're done. That's literally all there is to this. Pretty cool. It works with the other ones too. Let's do another one. Let's do one with a cubic. Let's do x minus 5 cubed. You know what? I'm going to leave it like that. I'm not going to put a number outside. Now you try that. See what you can do with it. All right, now this one looks slightly different than before, but you remember that the number on the outside is the number that is the y coordinate. And there's nothing on the outside. So what's the number for nothing? 0. So I have 5, 0. That's where I start, which is 1, 2, 3, 4, 5 here. And I'm not plugging in numbers. I'm just memorizing the points that I used from the parent function. And I remember from the original that these 2 dots were the ones that were colored in. And then from there, I just drew a shape like that and a shape like that, and I'm done. That's all there is to that. Pretty cool. All right, let's try another one, kind of along the same idea. Now, I highly encourage you to try this one. It's important that you understand what's about to happen. Try this one first. And even if you don't get it right, that's okay. But I want you to try it because a lot of people will get things like this wrong. Okay. Now, I want you to notice, if you've already tried it before, hopefully you did, and you're back. Notice that there's no number in here with the x. Now, some people will say, well, then that means it's 1. Well, no, because while there is a 1 multiplied there, that's not what we're talking about. Because the number should be something out to the side of it, right? Like plus something or minus something. And there's not a plus 1, is there? That changes things. If you add 1 to something, it changes it, right? What would you do to not change that? It would be 0. There's nothing. I think of it this way. There's nothing in there with x. Nothing has happened to it. I haven't added anything to it. I haven't subtracted it. Nothing has happened to it. There's nothing in there with the x and the square root symbol. What's the number for nothing? 0. Not 1. 0. And the number on the outside, because see this absolute value sign didn't extend out here, did it? That means the 2 is on the outside. So the number on the outside we don't change. So this is 0, 2. A lot of people will swap those up and they'll say 2, 0 and put it like here, or even stranger, they'll put it different places. I'll also see a lot of things like Like I said, they'll think that's 1 because there's a 1 multiplied there. So they'll put like 1, 2, something like that. That's also incorrect. So if there's no number in there, it's just 0, 2. Now, I've memorized the shape, and there's my square root. Just like that. All right, let's do another example. This is going to be a little different. This is going to be another variation you could see. All right, now if you think you know how to do this, give it a shot. But I will go ahead and tell you that this negative is going to do something. Now, what it's not going to do is change this. The rules for finding the vertex are always the same. So some people will see this and go, hey, does that change this stuff? And I have to make it a positive, then switch it back to negative? Don't do any of that. First of all, you can't distribute a negative into something that's squared. So algebraically, it's not even a thing you can do. But two, we're not doing math right now, so to speak. We're just doing pattern recognition, right? So don't actually multiply anything by negatives or distribute negatives. None of that stuff happens. You're just going to blindly do what you normally do, which means I'm going to do change this sign, don't change this sign. That process does not change whether you have a negative out in front or not. What that negative is going to do is change the shape of this thing. So the coordinate 1, 5 is here, 1, 2, 3, 4, 5, here. And remember, a quadratic looks like a parabola. It's that U-looking shape. Well, what this negative is going to do is it's going to take all the answers and make them negative. It's going to flip them upside down. So when you have a negative out front, it's literally going to take this shape and flip it over. Now, if you're wondering where I got these dots, I didn't think about the numbers. I just thought, oh, it's over 1 down 1 and over 2 down 4 from the original dot. I just memorized that configuration. Whether it's upright or upside down, it doesn't matter. The configuration is the same. And that's where that comes from. You can also do this with square roots, and you can also do this with cube roots and cubes and absolute values and make those upside down. Let's do another one that's upside down. Let's do this one. This is an easy one. Let's do that. Try it if you're feeling confident. Oh, wait a minute. I didn't make this different yet. The whole idea was to put the negative out there, right? All right, try that one. All right, so again, the negative doesn't affect anything. I go -2, 4, and I have this number here. That's the point. And remember, the absolute value normally looks like this, right? It's the 45-degree lines going out both sides. But this is negative out front, right? This one. That means that it's going to flip upside down. Let me actually write that. I didn't actually write the words yet. Upside down. So now instead of going up, it's going to go like this. Just like that. Very simple. What about square root function? Can I do the same thing with a square root function? Of course you can. You can do this with any function. You can make up your own. I could do a negative square root of x minus 3. All right. So the number in here with x is 3 because I've swapped it, right? The number on the outside, well, there's not a number on the outside. So what is it? 0. That means it goes here. That's easy enough if you remember how that works. And again, this negative here in the front tells me I'm going to flip it upside down. What does that look like? If you haven't drawn it yet, try it on your own, because if you see it, then it kind of spoils it. I have found in my experience that when you ask people to flip a square root function upside down, they usually give me, I've seen a lot of interesting results. So I would try it first just to see if you've got a grasp on what that looks like. All right, this is what it actually looks like. Normally the dot is up here, so I'm going to flip it upside down and it ends up right underneath. And the other dot's usually over here, so I'm going to flip it underneath to here. Instead of over 4 up 2, I'm going to go over 4 down 2 from the original dot, and I get that shape. Let me draw it a little better. And that is what that negative square root thing looks like. Okay, there's one more concept I have to show you. I don't know how long this video is. I'm sure it's getting kind of long, but you do need to see how this works. If you need to pause the video and come back for round 2 or take a break, this would be the time. I'm about to show you the next concept. It's just something else that you can do with these functions. All right, what happens when I end up with a number out front? A coefficient in front of the parentheses or the square root or the cube root or cubic, whatever it is. You have a number out front. Well, it's going to do something to it. What it's not going to do is change what this first coordinate is. So I can still go -1, -3. I'm still going to do the same thing here. This has not changed. Okay, I need you to understand that. Finding the vertex, the new starting point, is not different. You're still going to swap the number in the parentheses. You're still not going to swap the number on the outside. None of that changes. What is going to change is the way you're going to draw the rest of the dots. If you think about it, whatever number I plug in is going to be multiplied by 2. So that means the height, the up and down numbers, are going to be multiplied by 2, every single one of them. No matter what I plug in, the height is now doubled. That's what this 2 does. It doubles everything. So where I did go over 1 and up 1 here, right? I usually do over 1 up 1. I'm going to double that height. So instead of going up 1, I'm going to go up 2. And same thing on the left side. If I go left 1, normally I would just go up 1, but I'm doubling that. It's instead of drawing 1, I'm going to go up 2. That's what that looks like. By the same token, if I normally would go right 2 and up 4, right, to this point, I'm going to double that distance. This is why you can't count from this point. You need to count from the original if you're going to do this doubling stuff. So if I go over 2, now I'm going to go up 8, which is up here. Right? 1, 2, 3. Yes. That doesn't matter what that point is. The point is it's 8 up. Right? It is double the original distance. And same thing on this side. And so what that effectively does is takes that parabola and it stretches it upward. Okay? It makes it kind of thinner and taller, if you will. Not technically taller, because they're all infinitely tall. They keep going forever and ever. But it has this effect of squeezing it and stretching it up taller, faster, I should say. It grows faster. By a factor of 2, in fact. That's what that does. Now, do you have to draw these dots up here? Not necessarily. Really, what I'm looking for is when you see a 2 here, you know that it's over 1 and up 2. This is kind of where that shape takes shape down here. And that also works with other things, like you can do it with absolute values. You can do it upside down, all kinds of things. Let's do an absolute value. It works the same way. Let's do y equals 2 absolute value of x minus 2 plus 1. Now again, this 2 out front doesn't affect where I start. 2, 1 is where I start. Swap the inside, didn't swap the outside. I go right here. This is my starting place. Normally I go over 1 and up 1, over 1 and up 1, over 1 and up 1. That's what I usually do with this absolute value function. But here I'm doubling all the heights. Now a lot of people will go over 2 and up 2. Now that's not correct. You're always going to go over 1 every time you do this. Over 1 and then up 2. And then over again and up 2. This is exactly what the slope is. Because this is linear, in a way, you actually end up getting the same thing you get with slope. This is 2 over 1 slope. It's the same thing. That's what it is. So it takes that normal, actually I can draw it for you if you'd like to see it. The original looks like this, doesn't it? 45 degrees. This is what that original absolute value looks like. And when you put that 2 in, it takes it, it kind of pulls it upward. You think about like stretching it up, and it makes it skinnier in that process. It's not making it skinnier, it's pulling all the dots up, which effectively stretches it thin. Right? That's how that works. You can also do this with, well, you can do it with all of them. You can do it with cube roots, square roots, everything. Let's do one more, just to make sure you've seen that. Because this one can be a little odd. Let me actually do it with just the most basic one. Y equals 2 square root of x. So I'm not going to do any kind of modifications to the where it starts. Where does this thing start? Well, this is just the parent function times 2. In other words, there's 0 in there and there's 0 on the outside. So I'm starting in the middle still. All right? I'm going to use this example. And if you want to try this, I would suggest trying it on your own first real quick. But I'm going to show you how this affects it, because this is a little bit different, or at least it seems different. But it's not. It works the same way. You're going to take the height numbers and double them. So if I have, normally it goes over 1 and up 1, right? And then over 4 and up 2. I'm going to double those heights. Let me actually change color for the new one. So this one doesn't double, because it's double 0, 0. It doesn't go anywhere. But if you double 1, you get 2. If you double 2, you get 4. So you end up getting this taller, stretched out square root function. So let me kind of do this. So the green one here, that's the original. That's the parent function, right? The original. And when you put this 2 out front, it takes all the heights and doubles them. See how that doubles that distance? That's what that does. And it kind of stretches it upward. So even with something like a square root function, it takes the same thing, or does the same thing to that graph. All right, one more. I said this was the last one, but let me do one more, because I do want to show you how this works. What if you got something with a fraction? This is kind of bonus round. Let's do 1/2. Let's do x minus 3 squared plus 1. What if you had a fraction there? Now, if you want to try it, I would definitely not want to rob you of the opportunity to try this and see if you can get it right. It's actually really rewarding if you can figure out how to do this. But I understand that it's kind of confusing, because it is a fraction. What is it not going to change? Well, it's not going to change our vertex. Again, it's always the same thing. 3, 1. So that's easy enough. Well, this, just like before when I had a 2 there, it doubled it. Well, what I'm doing here is I'm cutting it in half every time, right? So if normally I go over 1 and up 1 here, now I'm going over 1 and up, well, half of 1 is a half. So I'm only going up half. Let me actually zoom in for you so you can see this. Don't be afraid to do this. This isn't like as bizarre as it seems. You may not have done this much, but you can. There's no reason why you can't graph things on half of a graph. Like that. Right? And normally the next one would be over 2 and up 4, right? It'd normally be up here. But half of 4 is now 2. So I'm over 2 and up 2. So I'm taking all the heights and I'm now cutting them in half. So my first one is 1/2, the next one is 2, and so on and so forth. And you end up getting this. And at this scale, at least, of course it gets complicated when you get into the theory of what actually is happening. We're not getting into all that stuff. But at least at this scale, if you leave all things equal, what it looks like it's doing is taking that graph and fattening it out, right? Because the original one was taller, right? It was more like this. That's the original. And so what we've done is we've taken it and squished it, if you will, kind of flattened it, kind of broadens those arms out. Okay, I think that's probably enough examples. The point is that if you take these shapes, and if you've memorized these shapes and the way the dots relate to each other, then you don't have to do much math really at all. At least what I'm calling math is, plugging numbers in and calculating them. None of that stuff. No evaluating these functions. All you have to do is find the starting point and then draw the shape. If it has a negative, you flip it over. If it has a number out here, okay, yes, you do modify the way the heights work. But again, even then, it's not complicated. You just either move them up or down. But all of these things are all the same, and they all come from the same uh, origin of changing where these things start and then just drawing a picture. All right. All right. Cool. I think that should be enough examples. Thank you for being with me to the end. If you made it this far, congratulations. Um, and in the next video, we're going to talk about a concept called domain and range, and then increasing and decreasing and things like that. But uh, but good job for getting through the graphing and stuff. And I hope you got a lot out of it. And I will see you guys in the next one.